So in this exercise, we're asked to find the expectation of L, where L is the length of an arc containing a point in a circle, in the unit circle, to be more precisely. So here we are said, given the information that the unit circle is divided into 3 arcs. We're choosing 3 random points, A, B, C, on the circle, independently and uniformly. And we are forming arcs between A and B, and A and C, and between B and C. And so L is the length of the arc that contains the point 1, 0. Okay, so what does this mean if we think about the following? So let's draw a circle, something like this, and we have the following axes, x, y, and now that became a little off, so let's draw it in the middle. That's it's a little off, but you see what I'm trying to get at. So this is x and this is y, and the point 1, 0 is just here. This is the point, x equals to 1, y equals to 0. Okay, and the length, and let's think about A and B. Let's just say we drew point A and it just landed here. This is point A. And then we drew point B and it landed there somewhere, and then we drew point C. So now we have an arc going from A to C, like that. We have another arc going from C to B. All right, that's a little ugly one, like this. And let's draw another one. Let's take purple here. Okay, so we have 3 arcs. We have this arc here, we have this arc there, and this arc here. And in A, we're asked to explain what is wrong with the following argument, where the total length of the arc, which is 2 pi, so the full length is 2 pi. So, and then the so by symmetry and linearity, each arc has a length of 2 pi on average. Okay, and so referring to the arc containing 1, 0 is just a way to specify one specific point, so one specific one of the arcs. It wouldn't matter where if it's 1 or 0 or 0 minus 1. And so the expected value of L is 2 pi divided by 3. Well, it is true that each of these arcs are on average 2 pi divided by 3. The thing is that it's not true that this point or this arc that contains, well, it's actually, there's another arc here that I need to specify just to point out. I mean, in this specific case, L, let's draw L here, and this, in this specific case, L is this arc, A to B, yeah? But the expected value of L is not 2 pi divided by 3. And why is that? Well, one way to see this is that it's more likely that this point will end up being in a longer arc overall. So it's more likely that this point, or L, designating the arc that contains this point, will be larger on average. So it'll be larger than any of these arcs that I've drew here. So it has to be the case that L is not 2 pi divided by 3. And so in the next question, we're asked then to figure out what this part of the this L arc is. Okay, so let's dive into that question now immediately. And here in B, we're asked to divide the arc that contains this point, which is what we called L, and the piece extending counterclockwise, so going up in this direction. We call this L1, and the piece extending clockwise, so going downwards here, is L2. And we are asked to find the CDF and PDF and the expected value of L1. Okay, so how should we think about this more precisely? Let's just write down what information we given. So we have L equals L1 plus L2. Now let's start by thinking about what the CDF of L1 is. So the CDF, start with that. The CDF of L1 should equal the probability that L1 is less than, and I'm just going to choose X here, little X. So any value on the circle, and X, I should say, X goes between 0 and 2 pi. So the length is always larger than X, so it's somewhere on this point, and it is just below 2 pi. It can never reach 2 pi because we will have points outside of where A, B, and so if you have A and B falling into a very large arc, C has to fall somewhere else in that remainder of the length. And we draw these points independently and uniformly. Okay, let me just move this piece of information up here. Okay, and now we need to think about what does it mean, where does L1 fall on this? So this is move this a little bit to the right. L1, let me take another color, take green here. L1, we said, is this piece here. Okay, how is L1 defined? L1 will be defined by any of the points A, B, and C falling on this line here. So we think about taking this full circle, and we are sort of extending it. And if A is the smallest point, so we think about A, B, and C. If A is the smallest point, then A defines the boundary for L1. If B is the smallest point, say it falls just here, right? If B is there, well then L1 will be this remainder here. Okay, so L1 is really the minimum. It will be the minimum of A, B, and C. Okay. So let's take this and put it in here. A, B, like that, smaller than C. And now, what does it mean that we have the minimum of? Well, the thing is that with the minimum, it's easier to think about the complement. It's easier to think about the complement because we want, instead of asking let me just draw this and I'll explain this in a bit. So minimum A, B, C larger than X. Now, by thinking about the minimum, it's now easier to say that basically A has to be larger than X, B has to be larger than X, and then X, sorry, then C larger than X. And that's why we take the complement, because then this statement has to hold true for all these random variables. And now we use independence. A larger than C. Okay. Probability of C larger than X. It's not ugly there. All right. And now we ask, what does it mean that, well, what is this probability here? Well, the probability of A being larger than X is, when you think about this being a random, a uniform, right? It's a uniform random variable, and it's larger than X, so it has to be 1. It's the complement of X divided by 2 pi. And all of these have, all of these terms are distributed in the same way, so we have 3 power to the 3 here. Okay, and just to be clear, this term here comes from the fact that we have a uniform random variable. So point A, I'm going to write it here to the right, is distributed uniform 0 to 2 pi, like this. And the CDF of A is then x 2 pi. Okay, and this is where this term is coming from, and this is the same for B and C. All right, so now that we have the CDF, we to get the PDF, we take the first derivative. So the PDF of L1 equals the first derivative of L1, which is, take the outer term minus x 2 pi, oh whoops, should be a 3, 2, and we have a minus from here, a constant disappears, and then we take the derivative of the inner function, which is minus 2 pi. Okay, and that whole thing is simply 3 to divided by 2 pi, 1 minus x power 2. All right, so that's the PDF, and now we have all the necessary components to calculate the expected value of L1. Right, so let's tackle that part of the question. So the expectation of L1, we have a integral from 0 to 2 pi. That's the support of L1, and if L1, we'll use x here, sorry, and then dx. Okay, and then we have the PDF we just calculated, 2 pi x. I'm going to copy this term here. Okay, that's dx over dx, and now we expand this full term here. We're going to take out this constant and put it to the outside. And yeah, we evaluate this integral after that. So 3 to pi. Let's calculate. We expand this term here. So that's x to the 1 minus 2x to pi plus x to 2 pi. Okay, like this. Now we're getting there, slowly and gradually. Now it's all about just expanding the terms. I'm sorry, we'll multiply in the x term here. Okay, so I'm going to just copy this, 2 pi. That's x minus 2x squared. I'm going to delete, factor out the 2's there, so we end up with a pi. And then we have x3 to pi dx. Okay. And now, by expanding this whole thing here, you can do the calculations yourself, but this is now from here, just simply this whole thing will reduce down to pi 2. So yeah, I mean these are just simple derivatives in terms of the power of x1, 2, and 3. And by expanding this and multiplying in this whole term, you see that this ends up being pi divided by 2. Okay, so now we're going to use, in the last part of this exercise, use information from B to find the expectation of L. Expectation of L. And we said that L is just L1 plus L2. And we use linearity in this equality here. So that's L1 plus expectation of L2. Now, it doesn't really matter if we, and we know that L1 is pi divided by 2, and by symmetry, L2 will be the same, has the same expectation, because, I mean, L2 is just going in the other direction here. So let's just be clear about that. So let's use another color here. So if this is L2 up here, sorry, L1 up here, L2 is just the remainder of of this term. So this ends up being L2, and now this, with the same reasoning, this part will be has the same expectation as L1. So we end up having then pi divided by 2, pi divided by 2, and this whole thing ends up being pi.